Developers often embrace JSONB for schema flexibility, but this choice immediately impacts query planning. A simple where clause on a nested JSONB attribute without proper indexing forces a sequential scan across the entire table, even if the table is small. Relational models, conversely, leverage B-tree indexes on discrete columns, achieving logarithmic time complexity instantly. The perceived ease of adding a new attribute to a JSONB column bypasses the crucial database design step of normalization. This trade-off is not about convenience, it is about latency. When dealing with high-volume transactional systems, the millisecond difference between a B-tree lookup and a JSON index scan on JSONB paths becomes critical. We must analyze the access patterns before committing to the document model within a relational database. The flexibility of JSONB is a performance debt if not managed correctly. JSONB is not merely a convenience feature, it solves specific integration challenges. Consider ingesting data from external third-party APIs, where the payload structure is volatile or unpredictable. Attempting to map hundreds of optional, frequently changing fields into a rigid relational schema creates maintenance overhead and requires constant schema migrations. Storing the raw payload in a JSONB column preserves the original data structure, simplifying the ingestion pipeline. Another mandatory use case involves user-defined metadata or configuration settings, where each user or tenant requires a unique set of attributes that cannot be standardized across the application. This approach isolates the volatile data, preventing schema sprawl in the core transactional tables. Effective querying of JSONB relies exclusively on generalized inverted indexes, or JIN indexes. For searching within the entire document content, a standard JIN index on the column is sufficient, using the containment operator. However, for targeted lookups on specific keys, we must use expression indexes. For example, indexing the path data, user ID allows the query planner to use a B-tree index on the extracted text value, significantly accelerating equality checks. The data arrow operator returns JSONB, while data returns text, which is essential for type-specific indexing and comparison. System analysts must define these specific paths upfront, treating them as virtual columns, otherwise the performance gains are lost. When comparing query execution plans, the difference between relational and JSONB access is stark. A relational join on indexed foreign keys typically results in an index scan or index-only scan, minimizing disk input-output. A JSON query using the JIN index on a specific path, while fast, still involves traversing the inverted index structure and potentially fetching the full JSON document to satisfy the projection. If the query requires filtering on multiple nested attributes, the planner must combine multiple JIN index lookups, increasing complexity. For queries involving aggregation or complex filtering across many rows, the relational model maintains a predictable performance profile because the data types are strictly defined and optimized for columnar operations. JSONB excels in simple key-value lookups, but struggles when the query needs to analyze the entire document structure repeatedly.
The primary integrity challenge with JSONB is the absence of native foreign key constraints, check constraints, and unique constraints on nested fields. This shifts the burden of data validation from the database engine to the application layer or database triggers. To enforce referential integrity for a nested order identifier, a before insert or update trigger must be implemented. This trigger executes a lookup against the related table, ensuring the referenced key exists before the transaction commits. For schema validation, PostgreSQL's check constraints can utilize JSON schema validation functions, ensuring the document structure adheres to predefined rules, such as mandatory fields or data types. Relying solely on application logic for integrity introduces race conditions and potential data corruption if multiple services interact with the database. Updating a small segment within a large JSONB document requires careful handling to avoid unnecessary overhead. A naive approach involves fetching the entire document, modifying it in the application, and writing the whole document back, which is inefficient and prone to concurrency issues. The correct method uses the JSONB.set function directly within the SQL update statement. This function allows atomic modification of a specific path within the JSON structure. For example, updating a user's nested preference setting requires only the path array, the new value, and the Boolean flag for creation if the path does not exist. This minimizes write amplification and ensures that only the necessary bytes are modified on disk, maintaining transactional integrity and improving write throughput. The most robust approach for complex systems is the hybrid model. Core, highly relational data that requires strict integrity and frequent joining, such as user identifiers, timestamps, and status codes, remains in standard columns with B-tree indexes and foreign keys. Volatile, non-standardized, or infrequently queried attributes, like user preferences, logging metadata, or third-party integration details, are stored in a dedicated JSONB column. This strategy ensures that the performance-critical paths leverage the relational engine's strengths while providing the necessary flexibility for evolving data structures. System analysts should define a clear boundary. If a field is queried in more than 20% of transactions, it must be promoted out of the JSONB column into a dedicated relational column. Migrating data between relational and JSONB structures is a non-trivial operational cost. Moving a field into JSONB requires a simple update using the JSONB.set function across all rows, followed by dropping the original column. Moving a field out of JSONB, known as promotion, is more complex. It requires adding the new relational column, backfilling the data using the hat operator, and then creating the necessary indexes and constraints. This promotion process often requires locking the table for the duration of the backfill operation in large datasets. Therefore, the decision to use JSONB must account for the future cost of refactoring, especially if the application anticipates high growth in data volume or changes in core access patterns. JSONB is neither a universal anti-pattern nor a silver bullet. It is a specialized tool. Adopt JSONB when the data structure is inherently schemaless, when the data source is external and volatile, or when the attributes are rarely queried but must be stored. Avoid JSONB for fields that participate in frequent joins, require strict referential integrity, or are subject to complex analytical queries involving range scans. The flexibility gained must always be weighed against the loss of native database optimization and integrity enforcement. System analysts must enforce a policy. If a nested JSONB field requires a GN expression index, that field is a candidate for promotion to a relational column, ensuring the database remains optimized for its primary workload.